Technical Committee on Induced Seismicity, along with Jens Lensny and Madi Haddad and Ahmad Ghassami. So our monthly webinars this month, we're very happy to welcome Rebecca Harrington, Ruhr University Bochum. Who's going to be talking about source parameters of induced earthquakes and impacts on lithological properties and mechanisms. So I'm sure this is going to be a fantastic webinar. Really looking forward to it and thankful to Rebecca for agreeing to present. Before we pass it over to Rebecca, though, just a few quick introductory remarks, and then we'll get into the webinar. Jens?
Okay, yes. So the usual introduction for upcoming speakers, we have 3 lined up. And these will all be the usual time, the first Friday of each month, August, September, and October at 10 a.m. US Canada Central Time. First of those is Amy Fox from Enlightened Geoscience, and she'll be talking about a geological and geomechanical perspective on induced seismicity in the Montney Play in British Columbia. And the 2nd of September, we have Julian Balmer from Imperial College London and Dave Eaton from the University of Calgary, and the 7th of October. Both of those talk titles to be determined. Okay, I'll go through what Madi normally mentions at the beginning. Just that everyone's welcome to share the invitation links, but if you'd like to be added to the email list so you get these in the future for each monthly webinar, please contact one of us. You'll be muted during the talk. Please do submit your questions. This is Teams, not Zoom this time, but through the chat there, and that way we can address them at the end. As you've seen, this webinar is being recorded, and this one will be uploaded onto the YouTube ARMA Induced Seismicity Technical Committee channel, where we have many of the previous talks uploaded as videos, and so you can subscribe there to see more. Thanks.
Excellent. So with that, we'll pass it over to Rebecca to go through her talk.
All right, thanks for the invitation. I guess you can probably see my PowerPoint screen now?
Sure can, yep.
Okay, great. So I want to first off just acknowledge all of the work from a lot of different people that has gone into what I'm going to show you today. So this is by and large a lot of work from a collaboration that I started when I was at McGill with Yajing Liu, and that work has been done together with a lot of help of postdocs and grad students, as well as our collaboration with Han Kao from the Pacific Geosciences Center. And also Stu Venables from the BC Oil and Gas Commission, and some work also that I have done together with the USGS with Elizabeth Cochran from the Pasadena office. And what I'm going to show you today is work that we focused on basically looking at source properties of earthquakes, and specifically looking at induced earthquakes because of the controlled conditions and tighter constraints that we have on a lot of the questions about stress loading as in comparison to sort of natural earthquakes. So I wanted, because I don't know if everybody sort of has a background in terms of looking at earthquake source parameters, probably a lot of you do, at least to some degree, have some sort of relationship to earthquake static stress drop. But I wanted to go through a little bit of a background first to kind of give you an idea of what our objectives typically are. I like this idea that Rachel Abercrombie formulated in her recent review paper in 2021, that earthquakes are sort of one of the largest dynamic crack propagations in the earth. And so on the top here, I have kind of a, oh, you can't see my mouse probably if I use it as a pointer. Is that correct?
That's correct. I'm not seeing it, Rebecca.
Okay. Is there a mouse feature I can use in Teams? Sorry, I'm used to using Zoom as well.
Yeah, I'm not aware of a way to do this.
Okay.
Or if you're not able to do it there, then I don't.
Okay.
Either way.
All right.
So,
well,
maybe right-click somewhere and see if it pops up. Otherwise, we'll just go with that.
Yeah. Okay. I guess not. Okay, well, anyway, I'll just describe where I'm pointing then. So, but with the figure on the top, this is sort of the ideal conceptual figure of a fault that we have with a steep dip angle, which is embedded in the crust. And you can imagine that when an earthquake happens, some sort of patch of that fault ruptures, and the slip is variable, where the arrows of different colors and different lengths are supposed to represent this sort of variable slip. And what we're looking at in the top figure is the slip that's happened after the earthquake has finished. And when we measure static stress drop with seismic data, we're measuring the difference before and after the earthquake. What I have shown on the bottom is sort of you can imagine this as the stress per unit slip per area on a fault surface. And we know that we could measure something like this in a laboratory experiment where we look at this sort of the dynamic drop in stress, which is shown by the solid black line during the slip process. And at some point the slip process stops, the earthquake terminates, but we don't really know with seismic data what that black line actually looks like and what the strength of the fault is, or the fault surface is, while that earthquake is going on. So what we're going to do with our study of earthquake source properties, specifically where we're looking at this source property static stress drop, is try to infer what the stress state on or near the fault looks like during an earthquake, from not only stress drop observations, but inferring information from other sort of geological clues. Okay, so yeah, and this value that we measure with seismic data, as I said, is just the difference between the stress before and after the earthquake. It could be that that solid line dips below the sort of frictional resistance during the earthquake, but we can't determine the details of that during the slip process with seismic data alone. So how do we actually measure stress drop in practice? Well, if we have a very large earthquake where we can make, let's say, for example, this is a plot taken from Lay 2015 on the right-hand side, showing a slip inversion for a rather large earthquake in Japan. And if we have, let's say, geodetic data or seismic data, we can see that there's variable slip on the fault surface, but we can kind of take an average of that slip over the rupture area of the surface and calculate an average stress drop if we can observe it directly. But in order to be able to do that with some sort of slip inversion or geodetic data, earthquakes need to be generally rather large. So the way that we do it for smaller earthquakes is that we assume that we're dealing with a point source process, at least with respect to the wavelengths and the distance at which we're observing the earthquake data. And we look at the P waves and the S waves for a particular seismogram. And I have an example here on the top right of a seismogram for a small earthquake. And we look at its spectral information, both in the time domain and the frequency domain, and we make inferences and assumptions, and then we can calculate that average stress drop, much like we do for the larger events. And so how exactly do we do that? Well, we get that information from a seismogram. And if we were, now I'm highlighting I'm looking at one individual component of ground motion here on the top. So that's the time series of the ground velocity that we would measure. We can convert that to displacement. And we can look at the spectrum, or look at the information in the frequency domain. And you see, if you look at low frequency, so I have frequency on the x-axis and I have some sort of amplitude on the right, or on the y-axis. And at low frequencies, the amplitude is flat and constant, and that's going to be proportional to the size of the earthquake or the seismic moment. And then where that spectrum, if we start to look at higher frequencies, sort of bends over and starts to fall off or decay, that point at which it falls off or decays is the corner frequency. And it's inversely proportional to the duration. And so if we think about a fault patch rupturing, we would consider the fact that the fault is going to rupture with a certain duration, which I'm calling tau right here. And that duration is going to be inversely proportional to the rupture velocity. And that duration is also going to be inversely proportional to my corner frequency that I can measure and fit with my seismic data. So generally, I take my seismic data, I try to get a very good fit of that corner frequency, and then estimate that duration. And I can make assumptions about rupture velocity being constant because we don't have any reason to believe that, whoops, I think you lost my screen, right?
Yes, now I see your desktop.
All right. Let's see.
Wait a second, I'm seeing a Windows desktop.
There we go.
Okay, it's back.
Okay. Right. So if we have we have spectral information, we do our best job that we possibly can to fit that corner frequency, and then we can use that corner frequency to estimate our stress drop. And I'm showing the relation quickly here of how the corner frequency is related to stress drop. It's directly proportional, but the corner frequency is raised to the power of 3. So you can imagine that in my stress drop estimate, which is extremely relevant for things like seismic hazard estimation or the energy that we anticipate for particular earthquakes in a particular area, that is very strongly dependent on corner frequency. So any error in my corner frequency estimate is going to be propagated into my stress drop estimate. And because it's raised to the power of 3 in this equation, the corner frequency estimate or the stress drop estimate is much more sensitive to the corner frequency estimate as compared to the estimate of seismic moment. So that begs the question of how does corner frequency scale if we have a lot more smaller earthquakes relative to larger earthquakes? Is there a predictable relationship? And according to sort of theoretical considerations, there is a predictable relationship. And that's convenient to know because we have significantly more smaller earthquakes than we do larger earthquakes. So particularly in cases of induced seismicity where our background or historical background seismicity rates are low, we want to be able to use information from those smaller earthquakes to extrapolate and make inferences about how the ground would behave if a larger earthquake occurs. And then if we ask how that relationship is between corner frequency and moment, or another way to say that, how does stress drop change with moment? The theoretical considerations suggest that stress drop should be constant, more or less, with magnitude if the rupture velocity doesn't change. And there's no good reason to believe that the rupture velocity should be magnitude dependent. And so looking at data over the years, that's been a somewhat controversial claim, probably could say it still is, particularly for smaller magnitude events. And then people in the past have looked at things like mining data and found that, or were initially sort of with initial observations thought that stress drop may decrease with magnitude. By revisiting the data sets and using different analysis techniques, it seems to be that stress drop, even for smaller magnitude events, is relatively scale invariant. And so this comes from this review paper that I mentioned by Rachel Abercrombie in 2021, where if you look at the plot on the left, she is compiling stress drop estimates from a number of different studies, different types of earthquakes, showing that stress drop does seem to be more or less constant over 20 orders of magnitude. Now, when I say more or less constant, what you might notice is if you look at those isolines of stress drop, you'll see that they're varying themselves over 5-6 orders of magnitude. So while I say constant, we're looking at a log-log plot. And so the question is some of that variation real, or is that variation partially due to observational constraints? And the reason that question is important is if you take a look on the right and look at the assumptions of how you can translate stress, or use a few assumptions and translate stress drop to seismic energy, understanding those scaling relationships again is important for things like seismic hazard estimation, because the seismic energy is going to be directly related to the stress drop. And so how intense shaking might be for an earthquake of a particular magnitude is going to be related to the stress drop. So The questions that I'm going to try to answer by showing you some of the work, or the questions that we've been working on, and showing you some of the work that we've been doing in my group and together with Yajing Liu's group in McGill, are what do the differences in stress drop tell us about the faulting conditions? And in order to be able to answer that broader question, some of the more specific questions that we're trying to get at is the range that I showed you in stress drop values may or may not be real to some degree. And so we want to find out how observational constraints can affect our stress drop estimates. Also, we want to find out if these, in some cases, lower stress drop values that people have observed for induced earthquakes really are different, or if that's also related to observational bias, if there are differences between natural and induced earthquakes. And as a sort of spoiler alert, there are some differences in stress drop values for induced earthquakes as well as for natural ones, which we think are real variations and not just related to observational bias. And so we want to ask the question of, what do those variations tell us about the faulting conditions where those earthquakes occur? Okay, so I'm going to start with sort of the observational limitations of the source and kind of give you a little bit here also of theoretical background about why, even with optimal signal to noise ratios and optimal observational methods, we should expect some variation in the stress drop estimate that we have. So this is just from some figures from a paper by Yoshi Kaneko and Peter Scherer in 2015, where they have on the left different types of rupture models where you have a circular crack or an elliptical crack, and the rupture is propagating outward from the center or propagating from the side. And on the right-hand side, they're showing you the sphere sort of centered around the source volume, and the colors are representing different amounts of scaled energy. And just from the geometry of the source alone, we see that we have variations in stress drop depending on the azimuth or the point on the focal sphere. If you imagine a seismic wave traveling outward and radiating away with a ray directed toward a particular seismic station, that we're going to see some natural variation within the stress drop values. And so the question is, what kind of then station coverage and azimuthal coverage do we need to be able to see what's coming from the source and to be able to average that out and come up with a good, robust stress drop estimate? Now, there are observational limitations which are also based on not just the source, but the travel path that the waves take from the source to the receiver. So take this schematic drawing, is a little bit simplified, but it still shows some of the diversity in crustal material from wherever we have faulting conditions, where we see a fault core and a damage zone. And imagine you have an earthquake which happens on that fault, and you have waves which radiate outward. It's measured by your seismic station, which I'm showing as the little blue triangle here. And from those distortions or attenuation along the travel path as those waves travel through the damage zone or crustal rock with different materials, all of those are going to have an imprint on that spectral information as well. And it's not going to necessarily cause the energy to attenuate in that spectral plot to the same degree at all frequencies. And so we need to be able, the travel path is going to obscure what we measure, where if we could take a look at the spectrum on the left and assume that that's what it looks like without any attenuation, or this is just sort of a schematic idea that the attenuation is sort of diluting the resolution of what we can be able to measure. But the more stations we have and the closer we have them with better signal to noise ratio might give us more information on what the real spectrum looks like, which is coming from the source. So we did a study, this is together with my PhD student and Elizabeth Cochran from the USGS Pasadena office, where we took the LASSO data. So I think probably a lot of people are familiar with this data set. This comes from a nodal array of over 1,800 stations, which were installed in Oklahoma in 2016. And each of those little, for about 1 month time, and each of those little diamonds on the plot, the blue and the orange ones, represent one of the active nodes. And what you see with the dots there are the seismicity that happened during the deployment. And there were a handful of earthquakes which were large enough for which we could calculate focal mechanism solutions. So what we did was estimate source properties of as many of these earthquakes as possible with all of the stations which had sufficient data quality, and then sort of controlled for the fact by taking random selections of different nodes to sort of simulate a more realistic sort of standard type of observation with, let's say, 10 to 20 to 30 seismic stations, and see how taking a subset of those nodes and simulating a more, let's say, normal or standard seismic network, how those affect our stress drop estimates. So this is just showing some of the effects of station coverage. So I'm showing on the top the variation in the corner frequency from the spectrum and the seismic moment for a particular earthquake with the focal mechanism shown by the little beach ball plot. And the color bar on the left is showing the relative deviation from the average value for each of the nodes. And so you can see that there's quite a wide variation in those estimates of those parameters alone for just looking at the individual source spectra. And what I'm showing on the bottom then is a plot of what we refer to as the spectral ratio. And those are kind of getting into details that I don't have time for in the talk today, but it's a particular type of method which does a very accurate correction of those attenuation or path effects, where you can see that the individual lines are showing spectral estimates from an individual node, and where the color intensity gets brighter is showing overlapping estimates for or a higher intensity of nodes for the spectral estimate. And so the solid black line is showing the average from all of those nodes for this spectra or the spectral ratio between two events with the corner frequency estimate. So then if we take a subset of all of those stations and sort of vary our sample size of subset of stations, then we can examine a little bit what this deviation in the stress drop values that we measure for these individual earthquakes. So in these two plots, I'm showing results from single spectra, which is a sort of standard technique that people use, and then using spectral ratios when we have similar events. And the bottom or the x-axis is showing us the sample size. If we take a subset of 10 stations or 20 stations, 30 stations, 40 stations, and you can see the variations from the mean average estimates by taking a subset of these stations. And what we see here on the left then are the stress drop estimates, which are based on the single stations, which are the darker colors, and then these spectral ratios, which do a more accurate correction for the travel path. And it might kind of be somewhat alarming for you to see that, for example, if I look at the top plot and I look up and I take 1,000 random samples of, let's say, 20 individual stations. So if you look at the 20 on the x-axis, and I look at 95% of these 1,000 samples that I take, I can see that there's roughly about 35% in variation or deviation from my mean value. And 20 stations would already be quite a lot if you're thinking about a sort of local network of stations. So you would need 20 stations to be able to at least get an accurate stress drop estimate to within 35%. And of course, the more stations you have, up to 50 stations, that decreases that variation. But it's a sign that probably what we have previously defined as good coverage is not necessarily good when it comes to trying to place tighter constraints on our stress drop estimates. So if we want to increase precision of those stress drop estimates for either 2 sigma or 3 sigma of those estimates, then we probably need 20 stations or more. And what you also might notice is there are lines of different colors which show the maximum azimuthal gap of those stations. So not only do you need good 20 stations or more, but you need good azimuthal coverage to make an accurate stress drop estimate. Okay, so that tells us that we probably do have a lot more observational bias in our stress drop estimates than we previously anticipated. And that then brings us to the question of if there are differences between natural and induced earthquakes, and if so, what are the implications for the faulting conditions? So a lot of the work that I'm going to show related to this question is part of a project that we did where we installed a local seismic network in the Kiskatna area in British Columbia, and for a period of 3 years, from 2017 to 2020. And in addition, the BC OGC and the Pacific Geosciences Center also installed stations there. So all of the triangles that you see on the plot are this increased station coverage. You can see the length scale here to give you a sense of how dense these stations are. And all of the dots, or all of the hydraulic fracturing wells, are also shown on the plot with the solid lines, and the wellheads are shown with the squares. And then what you can see with the dots is the seismicity in the catalog from Roth et al. 2020 and Roth et al. 2022, which extends that catalog period up to the end of 2021. So there's a significant number, over nearly 8,000 earthquakes that we've recorded and located with meeting quality control criteria during this time, where the color bar is showing the time period of when the earthquake occurred. So, whoops, my mouse isn't responding. Just to give you a sense, a lot of these earthquakes seem to be induced, because what I'm showing you here is a histogram of the events over time. This is a figure from Roth et al. 2020. And the gray shaded areas are times of injection at individual wells. And so a lot of the seismicity occurs during the time of injection, whereas the blue curves, or sorry, the aqua curves is showing us the cumulative injection volume per wellhead, or daily cumulative injected volume per wellhead, and then the blue curve is showing us the cumulative seismic moment. And there's very little activity outside of the times in which the injection is going on. Now, a lot of these earthquakes, so we made a relocated catalog of the earthquakes for this data set, and a lot of these earthquakes seem to be occurring on what looked like either strike slip or reverse sense faulting, and they seem to be optimally oriented within the ambient stress field. So this is just an example at a particular well, which suggests that they occurred on pre-existing fractures. These are not, or faults. These are not necessarily directly related to the hydraulic fracturing process, because then we would expect them to highlight different sort of structural features. And the relocations suggest faults that are reactivated in the ambient stress field. So here are just some focal mechanism plots for some of these events. This is from Roth et al. 2022, where we see, as I said, in the northern part of the area, on the left, we see focal mechanisms which suggest a lot of reverse fault motion, whereas in the southern part of the area, it looks like we have a lot of left lateral strike slip faults which have been activated. So again, both of which are consistent in the ambient stress field. So there's been, as I mentioned, there has been some work done showing the stress drop values of induced earthquakes are suggesting that it is on average at times lower than natural earthquakes. But we very carefully estimated the stress drop of these events in this catalog using the spectral ratio approach where possible. And what we found is that many of the earthquakes have stress drop values which are indeed comparable to tectonic earthquakes, maybe on the lower end, but still ranging around values of 1 to 10 megapascals, which are shown by the green diamonds. And the size of the diamond has to do with how many similar events there are in a family, but not necessarily important for understanding the range of stress drop values that we observed. We've also done additional work a bit further north, just north of Fort St. John. This is work from Yu et al. From 2019 and 2020, where we had a dense deployment. So the regional map is shown on the left with seismicity in the region. And then on the right, we had a dense deployment of stations which were centered around a hydraulic fracturing well. and recorded for a roughly 7 week period to prior to and then following a hydraulic fracturing treatment, so that we could capture the features and seismicity associated with the fracturing treatment. And what we saw were two close clusters of seismicity circled here as C1 and C2, cluster 1 and cluster 2, as well as some additional earthquakes, which are plotted in white and also blue for nearby hydraulic fracturing wells. And we looked at the source properties, namely the stress drop of those events as well. And also using this very careful approach and applying very stringent quality control criteria, what we found is that you can see sort of the earthquakes shown on the left with hydraulic fracturing well 1, which is in the center of the plot on the right. And the color bar is indicating the stress drop value. And the events which are closer to the well indicate lower stress drop values. And I'll get into in a minute why we interpret that to be a real effect and not an observational artifact. Whereas the events which are outside the well exhibit higher stress drop values. And I should make a side note here that the events which are further away from the wells are probably not that well located, because the next nearest station was about 50 kilometers away. So the azimuth of where it is located from the well is probably not that well constrained. However, the distance likely is. So while we may not have good epicentral control, we do have a good sense that it's at least not close to the central well. Okay, and so that's mainly these events are the ones which are associated with the cluster 1 and cluster 2, which are right next to this hydraulic fracturing well 1, which is labeled on this plot. And so basically what we found, again, just to summarize here, is that the stress drop values were lower, closer to the well. What I'm not showing here, but which was part of this study, is that we also investigated the seismic quality factor close to the well and found evidence to suggest that it was also lower, closer to the well. And then that those two lines of evidence together suggested to us that the rock damage was probably greater toward the well, as was probably the pore pressure, which would suggest that the rocks toward the well are weaker in comparison to rocks, the crustal rock volume further away, which would be consistent with the hydraulic fracturing process generating large fracture networks. You would expect that the rocks should have lower elastic material properties. What was interesting when we started digging into the data set in greater detail is that we found a specific type of event which looked sort of different than the standard induced events, because for a particular magnitude, they had a very sort of extended, protracted waveform. So I have sort of a three-dimensional volume of the well that was the HF1 in the center plot shown on the left here. And then these earthquakes, typical induced events, and these what we call EAT-HWs, which were all happening in close proximity to the well, whereas the typical induced events had P and S wave pulses, which were narrower, which suggests that the duration is lower and it's probably information coming directly from the source, whereas these other types of events had wider pulses, for similar magnitudes and similar locations, which suggested that they had longer durations relative to their size. And so we looked in detail at their source properties and used the spectral ratio approach for a population of these different types of events that we saw to try to get very tight, robust constraints on what their corner frequencies were and what their relative durations were. And we did find evidence that these events had longer durations and interpreted that they likely had that meaning that they likely had slower rupture velocities. And if we look at the spectral ratios and the spectral fitting is shown in the top two panels here for those particular types of events. And then on the bottom here for the population event of these events, we looked at their duration as related to their seismic moment and found that they could be consistent to scale with sort of ordinary earthquakes, or that they, and it's within the magnitude range, we couldn't definitively say if it's one or the other, but it did open the possibility that these earthquakes scale more similarly to slower earthquakes that we observe oftentimes in the transition between brittle and the brittle plastic transition in fault zones, in subduction zones. So we interpreted that these lower stress drop values, or these wider pulse durations, these are sort of one and the same, applied a longer event duration or a slower rupture for these events, because if you recall back to that equation that I showed early on, that we have the stress drop as being related to the corner frequency, directly related to the corner frequency cubed. And then in the denominator, you see a constant multiplied by the shear wave velocity, and that is related to what we think is then the rupture velocity. And we generally assume that that is constant. So why does the lower stress drop then necessarily imply a longer, or lower stress drop imply a longer duration if we already make this assumption that the rupture velocity has to be constant? So then we had to consider for smaller earthquakes, because we cannot directly observe the rupture velocity, that could actually imply two scenarios. One scenario would be that the rupture velocity is the same for both populations of earthquakes, these typical earthquakes and these EHWs, but that the stress drop is low, so the actual ratio of slip to the fault length could be low. Alternatively, the stress drop, or the ratio of the slip to the fault length, would be the same for the slow earthquakes as it was for the typical induced earthquakes, but in fact that assumption of a constant rupture velocity would have to be violated, and that the rupture speed for those events would be lower. And so we opted or made an interpretation that would be consistent with the second scenario, where the rupture velocity would be lower. And so here I'm showing the spectral information, the spectral fitting again on the top plots, but on the bottom plots, I'm showing the inferred seismic moment of these events. And on the left bottom, you'll see the inset that these inferred slower earthquakes were actually occurring mostly closer to the wellbore, and seemed to have lower rupture velocities if we assume that the stress drop was the same, which would also be consistent with the lower Q measurements that we made in the 2019 study, all of which would be consistent with the second scenario of the stress drop being the same and the rupture velocity being lower. But either way, both with scenario 1 or scenario 2, they would both be consistent with having weaker rocks near the wellbore, where perhaps we've either overestimated the shear velocity, or in fact, if shear velocity is the same constant proportion of, if the rupture velocity is the same constant proportion of the shear velocity, then indeed those events would rupture more slowly. So this would be, if we go back to that plot here on the bottom, looking at the scaling for slow earthquakes as opposed to ordinary earthquakes, if we think about these EHW, or this special population of events occurring closer to the wellbore, there have been recently modeling works which suggest that the aseismic slip could be something which occurs near the wellbore where pore pressures are high, and could also drive or induce seismicity further away from the wellbore as a secondary kind of triggering process. And so our interpretation is that these EHW events could in fact be a manifestation of kind of a continuum of slip speeds. If you have aseismic triggering close to the wellbore, and these are happening on the margin or the sort of edges of a region of aseismic slip, and they would have lower rupture velocities, which are not quite reaching the rupture velocities of typical induced earthquakes. And in that sense, they look a lot like volcanic hybrid events, which happen in volcanic regions, which are sometimes interpreted to also be sort of the slower rupture of or slower earthquake rupture in kind of weaker, less coherent volcanic rock. And it would be sort of a similar scenario where we have earthquakes near the sort of edges of the damage zone from the hydraulic fracturing activity, which could rupture with slower rupture velocities. So to go back to those questions that I put forth initially, and to just kind of summarize here, how do our observational constraints affect our stress drop estimates? Well, our work with this nodal seismic array is suggesting that we probably have to change our definition of good coverage, and that in regions where we have low seismicity or low historical seismicity and only small earthquakes to work with, if we're going to estimate stress drop values and try to use those for seismic hazard estimates, which is a challenging thing to do, especially in regions where we have induced seismicity and regions of low historical seismicity, that we're probably going to have to increase our coverage in order to place tighter constraints on those stress drop estimates. There's no compelling evidence to state that natural and induced earthquakes may be different. And in fact, lower stress drop values for induced earthquakes may not be a good discriminating factor. But when we do observe lower stress drop, and it's probably spatially variable, I should say, but where we do observe lower stress drop values, it might be compelling evidence for variation with rock strength, and probably more likely happens closer to the wellbore, where the rocks are anticipated to be more damaged. And so it's kind of interesting to take these stress drop variations and their spatial and temporal variability, and together with what we know about the geological conditions, and make inferences with those different types of data together about what the variations in fault and geological conditions are. But it's going to take, as I said, sort of high resolution data and high resolution observations in order to interpret these kinds of data in any reasonable way. So just to kind of summarize and provide an outlook of where I think would be an interesting avenue to pursue, if we want to tie our stress drop estimates to geological observations, then it's probably a good thing to look at the geological record, the rock record as well, and try to get observations where we can, which is definitely challenging, of ratios of slip to length, because this can sort of tie our present observations of earthquakes and go beyond the limitations of what we can observe with seismic data to things like fault geometry and fault roughness, and give us observations over a broad length or a broad range of length scales. So if we want to learn more about source differences between slow and fast earthquakes, I think this is also an interesting avenue to pursue, because as I said, there has been some recent modeling work which suggests that there is a continuum of slip speeds, and our work with these EHW or sort of hybrid looking earthquakes would suggest that in fact this real continuum goes from the seismic energy band, maybe below that where seismic energy is not generated, and might kind of provide clues about the spatial limitations of where slow and fast slip is happening on faults. And all of this, I think, has potential impacts for induced earthquakes, of course. But what I think is also an interesting question, just from a sort of basic scientific research point of view, is by looking at these observations in this controlled environment using induced earthquakes, it can maybe help us answer big picture questions, which are more related to things like what are the factors or the rock strength conditions that determine when slip is slow on a fault versus when it's fast, and can certain faults have slow and fast slip at the same place at different times. So with that, I will conclude and take any questions you might have.
Well, thanks, Rebecca. That was a really interesting presentation and a really great overview. So thanks for going through that. There's a couple questions on chat. I can read them out, Rebecca, so you don't have to read and answer. But maybe while others are kind of thinking of questions, I'll maybe kind of kick it off if I could.
Okay.
I'm curious about the distinction between the fast or ordinary events close to the wellbore and the slower events further away. And I'm wondering if you got any thoughts in terms of a pore pressure kind of model. Given the fact that these are hydraulic fracture induced, there's obviously extreme net pressures close to the wellbore exceeding minimum stress, whereas with time that's going to that pressure is going to leak off, and you'll get likely a lower pore pressure plume moving out. So do you think there might be a pore pressure relationship to that distinction?
Yeah, so part of, just to clarify, I'm not sure if I think for this particular plot, these typical induced events and the EHWs, they both happen in close proximity to the wellbore. So you see both kinds of behavior. But I think your question was probably more related to just in general with high pore pressure near the wellbore. And the answer is yes, for sure. I mean, in this 2019 study, I don't know, where did I have the slide? That we did, this one, we first initially looked generally at these earthquakes and did some very straightforward poroelastic modeling. And what Hong Yu, that's my postdoc at the time, she found that there was definitely a sustained pore pressure increase, which acts within 1 kilometer very distinctly of the well, and then up to 5 kilometers from the well. Beyond that, you would have to explain sort of the generation of earthquakes with some other mechanism, whether it be poroelastic modeling of something, poroelastic stress transfer, especially if things are happening on a short time scale. Yeah. If there's some sort of delay, or the time scale that you're looking at could help to provide clues what a triggering mechanism could be.
Yeah, I guess just for context, it's probably obvious the direction I was going with this, but if we could understand that, maybe there's a mitigation approach to maybe, control the injection to drive more to slow slip, low,
yeah,
assumably more lower hazard type events. Excellent.
Yeah, I mean, that's kind of where I was going with the last point that I made, that if we can kind of figure out what are the conditions that keep slip slow or fast, maybe it's then at some point possible to just adjust parameters so that it only stays slow.
Excellent. So in the chat window, Eddie Siebert's asked a question going back to the station coverage observations you made. And he's wondering if you had looked at a synthetic model, and if there's a way to do that with sort of a forward model to take sampling of stations to understand the impact of coverage.
Yeah, I mean, that's essentially what Kaneko and Shearer were doing. They're using synthetic models to look at sort of to look at sort of how heterogeneous the energy distribution is on the focal sphere, for example. And then you could, I mean, if you wanted, you could surely take stations at different azimuthal coverage. You'd have to sort of use some sort of velocity model, propagate those waves through, and then make inferences. But essentially, that's what we did empirically with the LASSO array. We just wanted to make use of this coverage of over 1,800 stations without having to sort of simulate any sort of velocity model and then see what the effects were. But yeah, I think it would still be a useful exercise to also, especially if you wanted to design a particular sort of array for monitoring purposes, it would be a useful exercise to go through some sort of synthetic study like that.
Excellent. And then moving on, Adam Begg has a couple questions. So Adam's wondering how much lower the velocity was for the near wellbore EHW rupture velocities as a fraction of the shear wave velocity.
We played around with that. I mean, the thing is in terms of estimating the stress drop, you have to assume, let me find that equation again. You have to assume a shear wave velocity. And so if you assume a shear wave velocity, usually you use your best velocity model. And Hong Yu played around with sort of what kind of velocity changes would you need to be able to explain the variability. And that's kind of related to these plots a little bit. But she, if I remember correctly, I think she came up with velocity variations of about 20% to be able to explain the differences in stress drop, if you assume that the stress drop is the same. and as I gave you sort of scenario 1 and scenario 2 here, but there's also not necessarily any reason that you couldn't have a combination of the two.
And Adam has another question before I get to it though. Your acronym EHW, does that imply some mechanism, or is it what's the meaning of that acronym?
Oh, we were just trying to, initially we called them hybrids. And so we were, based on reviewer comments, because they were getting confused with volcanic hybrids, and we didn't want to imply that it's the same type of mechanism, we came up with the acronym, which we use in the paper. So, and to some degree, it's a little bit contrived, but it's just to be able to differentiate them from volcanic hybrids from a mechanistic point of view. Okay,
thanks. So Adam's also wondering if directivity is playing a role in the variations in the static stress drops.
It could very well possibly be, which is definitely suggested by that Lasso study. But we wouldn't be able to sort of, with the coverage that we have, because these events were so small and the number of stations that had good signal to noise ratios, it would be difficult to definitively say one way or the other how strong of a role directivity plays.
Okay, great. And then moving on, Chengao Li has a couple questions actually. One is there are more events around the HF1 well than HF2 and 3 in that. Sorry, we're making you go right forward and back through your presentation. Is that related to the relative structure between those wells, or is that just a instrumentation bias?
Yeah, I would say that's probably, yeah, I can't say for sure, but I would say that it's probably more related to the instrumentation bias, because as you see, the little red sort of maroon rectangles are where we had our stations deployed. And the other stations that were available were regional stations. So the events that you see here on this plot are those which surpass signal to noise quality control criteria and were able to be located. So, I mean, at HF3, you're not looking at distances which were all that much different than the other wells. So it could be a little bit related to structure, but I don't think that we have I don't think the data allows me to say that with confidence. Let's put it that way.
Excellent. Then Chengao is also asking if you think I guess it's more of a geomechanical question in terms of the critical stress state. So do you think these are critically stressed features and requiring low pore pressure? Maybe it goes back to that initial question I asked as well.
Yeah, I mean, not necessarily based strictly on this data set, but based on other work that we've done looking at remote dynamic triggering in this area, we found really low stresses on the order of tidal stresses, which seem to have triggered from remote earthquakes, remote main shocks, where the surface waves are passing through the area. And then there's a direct correlation between changes in seismicity rate and the passing of these surface waves. And the nice thing about looking at the surface waves of those distant earthquakes is that you can convert the ground velocity that you measure to stress perturbations that cause an earthquake to happen. And so we do see statistically significant increases in seismicity corresponding to stresses on tens of kilopascals. So on the order of tidal stresses, which would suggest criticality and that the structures are, at least in some cases, critically stressed.
Okay, there's another question in chat, but I had another question, and it's kind of relevant to the slide that's up at the moment. So maybe I'll ask my question so you don't have to jump around between all your slides. I'm curious on uncertainty and the depths and the potential impact on the stress drops. And, this is kind of a striking example to me where close to the well, you've got relatively shallow depths, and then the depths increase as you move away from the wellbore, which is also obviously moving towards the edge of the arrays. So could you comment on depth uncertainties and how that could tie into stress drop variability?
Yeah, sure. So yeah, the uncertainties are shown on the plot here with the whisker plots. And definitely the location uncertainty increases. You can see from the coverage on the right that away from the wellbore, those events which are white have much greater hypocentral uncertainty. However, if I go back to that equation of for the stress drop, the moment is going to be linearly dependent on R, but the stress drop is only linearly dependent on the moment, but it is, again, the key factor, or the most important parameter, which is influencing the stress drop estimate, is that corner frequency estimate, and because of the fact that it's raised to the power of 3. So we played around with that too, just sort of using all different, the range of location values, and it doesn't cause the stress drop to vary that nearly as much as the corner frequency, changes in the corner frequency does.
Excellent. And then returning to chat, Ben Doolan has 2 questions. The first one's probably relatively a lot easier than the second one, maybe. Can you comment on the magnitude range for the data set? I think he means that BC example.
Okay, there are 2 data sets in BC. I guess probably means the one for the EHWs or the one in near the Kiskatna area.
Yeah, either, whichever you
okay.
would like to comment.
Because it's quite different. So the one in
or
both.
This
this one is more or less below magnitude 2. And then the other one in the Kiskatna area, this is, you can see the moment of completeness. The largest event in this sequence was a magnitude 4.5. And then we have our magnitude of completeness is 1. So we have smaller events than 1, but 1 is our magnitude of completeness.
Excellent. So as I said, the second question is maybe a little bit maybe more topical. So he's also asking whether or not you think the triggering mechanism is pore pressure changes or pore elastic stress changes. Any thoughts, any comments?
Yeah, so also part of this study in 2019, I mean, it's probably yes in both cases, but it would depend on the timing of injection and the distance from the point of injection along the wellbore. So if you were far away from the point of injection or not a lot of cumulative fluid volume has been injected, it's very difficult to explain it, especially on sort of very short time scales with pore pressure changes. Then you need to invoke the poroelastic stresses. In this poroelastic modeling that Hongyu did for this study close to the wellbore, the pore pressure stresses are dominant. So definitely close to the well, it probably does play an important role. Further from the well at larger time scales, that's a more interesting question because I mean, poroelastic stresses should more or less act instantaneously, but there's modeling and now some observations too, some INSAR work that's been done, for example, by people in Canada, Iyer et al. And so on, that there does seem to be some aseismic deformation that's associated with the injection. And there's good reason to think, though, with that with the aseismic slip propagation, those should then load nearby faults, which are outside of distances where pore pressure changes would be expected to be significant. And that probably plays a very important role in terms of changing the sort of delta CFS, if you like, from that aseismic slip, which may be a mechanism that we have not been able to explore in great detail yet, because observing this aseismic deformation is pretty challenging, especially if it's not that big where it generates a geodetic signal. But I suspect that it's probably more important than we realize.
Excellent. Well, this takes us to the end of the scheduled hour, and we've gone through all the questions on chat. So take the opportunity to thank Rebecca again for the excellent overview. One one of the difficulties with virtual meetings like this, everybody can't show their appreciation with a round of applause, but I'm sure there's a virtual round of applause taking place.
Oh, thanks you. Thanks for having me.
And Jens is clapping at least. And just a reminder to everyone, Amy Fox will be giving the next presentation August 5th, the first Friday in August. So stay tuned for the invitation to that webinar. And Rebecca, we often have informal discussions. If you have a few minutes, if you want to stick around, we welcome people to unmute themselves and have more informal discussion.
Okay.
Again, thanks everyone, and have a great long weekend. If you're in Canada or the US, happy Canada Day or happy July 4th. Well, that was great. Thank you, Rebecca.
Oh, thanks again for the invitation. It's nice to stay in touch.
You've gotten a
the
few,
other side of the
thank
pond.
yous. Alexandros Savitis is thanking you, and you were also thanked earlier by Adam Begg and Ed Siebritz.
And external, whoever external is. It's a few anonymous logins, I guess.
And Chung Ho Lee. Yeah. Yeah,
the IR paper, that slow slip from Infer, is kind of interesting. I think there's interesting observations too, just from wellbore stability point of view. Ovintiv, we operate in the area. We've had some wellbore deviations that are maybe we aren't able to tie to individual seismic events, so it's probably more of a slow slip tendency.
We were chatting with Dave Eaton. When was it? I forget now. But I think, was it a conference? Probably when they were working on this, and they had also mentioned he has a lot of contact with the operators, I guess, as you know, and he had also mentioned that they had documented observations of wellbore deformation with no corresponding seismic signal. But
yeah,
I suppose,
absolutely.
I think it's probably more ubiquitous than we realize, just because of the difficulty in being able to observe it.
Right. Well, some of those images you showed, particularly the one with several wellbores and all those lineations going past, it's maybe not surprising that if we're having the tectonic or the shearing of those faults, that there's obviously going to be impact on the wellbores.
Yeah, that's true.
And the impact you mentioned on coolant failure stress of faults is an interesting one too, because normally we're seeing well-oriented faults within the stress field failing, but then sometimes there's something anomalous, a fault that's not well-oriented, and it's hard to know, well, is there an error in the stress orientations, error in the fault orientations, or is there something else going on?
Yeah.
And I think it'll be that's a very helpful avenue potentially for understanding those faults that we don't really understand why they slipped at that particular time.
Yeah.
So there's just a handful of people left logged in here, I think, if I'm seeing the complete list, but anyone's welcome to unmute if they want to ask Rebecca a question. Well, if not, Rebecca, it's probably getting late in the day for you. So again, thanks for agreeing to do this. And look forward to keep in touch. Looking forward to following your research and seeing what other observations you come up with, especially when you figure out that mitigation side of how to control the operation for more slow slip. But
yeah. I guess that's a broad scale objective, but yeah.
Yeah. Well, I think there's an interesting question in terms of injection rate. So, there are these kind of slightly injection sequences that it'd be interesting to see if there's any cause and effect that way.
Yeah. I think some of these artificial intelligence approaches might be fruitful in that regard. So I'm interested to see where that goes too.
And maybe pairing with
studies come out.
with DAS, if you have a very localized, the right conditions, that could be helpful for detecting the strain as well.
Yeah, that's true. I just had a DAS delivered. I just bought one actually. But this is a completely new avenue. So now I have a lot of homework to do.
This is just the interrogator, or do you have the whole thing?
I bought an OptiSense QuantX interrogator, but the project that I had funded that hit the limit for my instrument budget. Well, I also bought a file server to be able to store all of the data that I anticipate collecting. But I'm going to apply for some smaller university grants to purchase some cables to design some experiments. But in the meantime, we'll probably just use we will use dark communications cables. So yeah, nice. It's kind of one of these blue sky, high risk, high gain kind of projects. So we don't have, it was more sort of like a new program grant. So we don't have sort of specific deliverables that we have to do. So in that sense, we're free to kind of explore different things, which is kind of nice.
Fantastic.
Sunday there was ARMA hosted a fiber optic strain workshop that was very interesting. Lots of interesting observations for sure.
Yeah.
Actually, Ovintiv just supported a project with Dave Eaton in the Montney, collecting some fiber data for his research group to to interpret and evaluate.
Yeah.
Yeah, we work closely with a number of research organizations, and obviously Dave's pretty active in the industry space.
Yeah.
All right. Well, thanks again, Rebecca. Really appreciate it.
Thanks for having me.
Thank you.
Well, have a nice weekend then.
Happy Canada Day.
Yeah. Bye.
Talk to everyone later. Bye.